Hello and welcome to this introductory video on RC circuits. So we've gone through in the previous videos, talked about very simple circuits where we had resistors or capacitors. We then built up and said, okay, we can also actually combine multiple resistors or multiple capacitors, but in this video we're finally going to start mixing them. So let's consider the sort of simplest case. We're going to have a battery. We're going to have a capacitor. We'll put a resistor as well, just all in series. All right. And the question is, what will happen? Initially, this thing's not charged. It's got zero potential difference across its plates. And then we're going to actually close this circuit. What will happen? Well, there's no potential here. And we do basically a Kirchhoff's loop law. Potential in across our battery, potential drop across the resistor, no potential here, so the potential drop across the resistor must be whatever the battery is supplying. So let's call that the EMF. So initially the potential difference across here is the EMF. And we can figure out the current then is just divided by the resistance, the EMF divided by the resistance, right? V equals IR. So I0, the moment we close this circuit, is just EMF on R. But what's going to happen a little bit later? Well, a little bit later, this thing is starting to charge, so the potential difference across here is smaller. So it's going to be I is going to be EMF minus whatever's going on through here, the capacitor's potential, and then divided by R again. Okay, so over time, the capacitor potential is going to get larger and larger and larger. And eventually, right, this thing will actually be charged to the same potential and it will shut the circuit down. At that point, the current will go to zero. So this is the idea of an RC circuit, that if I initially connect it, I have sort of the maximum current, and that is going to decay away until the capacitor is fully charged. And once it's fully charged, there'll be no more current. And then what I can do is take the battery out and replace that by a wire, so I can short circuit the battery basically. If I do that, then this thing will now discharge across that path. And in discharging, again, the current will start being sort of a maximum because there will be this was charged to the EMF of the battery. This will decay away, starting off with a current like this. And then the current will go to zero as the potential decreases across the plates. So that is the idea of an RC circuit, that you have this time-varying current that goes between the EMF on R and down to zero. Okay, so you connect the battery, the resistor, and the capacitor, and initially you've got to charge the capacitor. First bit is sort of free, so you're just going with the maximum current. But as you start building charge, it's going to squash that current down. Okay, so the current will have to decrease over time, as we've just said. Okay, so here is just a summary again. You start off with sort of the maximum thing, which is just the EMF divided by the resistance, but over time that current will go to zero, so the final current must be zero. Right, the actual way in which this current behaves, or the actual potential across the plates rather, as you're charging, is given by this expression here. The potential across the plates at some time little t is the EMF of the battery times 1 minus e to the minus t on RC. Okay, we can redefine this constant R times C as a time constant, or the so-called RC time constant. Okay, and all we're doing there is saying that if we write this instead as just that the V as a function of time is the EMF 1 minus e to the minus t on tau. Right, we'll just replace RC with this quantity tau. Put some brackets in to make our multiplication work. So if we plug in that t is equal to tau, then V of tau is just the EMF 1 minus e to the minus 1, which of course is the EMF times 1 minus 1 on e. What does that mean? Well, this number, we can evaluate what that number is. It is just 0.632, And so fundamentally what the time constant is telling us, how long you have to wait to reach 63.2% of that final value. So basically be 63% charged on your capacitor. Now you can play this game in reverse, as we said. If you didn't remove the battery and you just do this instead, then you're going to discharge the capacitor. Same sort of thing applies. You start off with a maximal current and then you go to 0. In that case, the potential as a function of time becomes this expression here. Starts off with V0, which is basically the EMF, and then it's times just the exponential part. Why? Because instead of doing 1 minus as we charge up, we are now just discharging, going down to 0, and so we just need that exponential decay. So that describes these things, but why would you make them? Why would you make an RC circuit? One of the really good things about this is that this is clearly has some nice characteristic timescale, which means we can use this for timing, and you can set that timescale by either playing around with capacitance or by playing around with resistance. It's easier to actually change the resistance, so that's typically what's done. Let's think about this for a second, and I leave it to you to think about. It's food for thought. How do you actually go about doing the changing of the resistance? What would be an easy way to make what is called a variable resistor, where you can just dial around the resistance